Okay. No, it's there now. Okay, so last time, what I said I did this time, just for variation, I decided to use a series stub, all right? Even if we know that in microstrip, it's difficult, I decided to do this so you get a sense of how you may design using coplanar waveguide. So last time we used, just to summarize, we are designing for noise and gain. And what we did last time is to look at the noise circles that you see here on the left. The group of the circles towards the left side are the noise circles. The ones, brown ones on the right are the gain circles, and the gain for the incoming GS rather is the gain that is produced on the input side, not the output side, not the GL gain circles. These are the GS circles that we had specified in the problem. And in fact, to show you the problem here, if I may, that was a low noise amplifier at 60 gigahertz that people did using here, using coplanar waveguide. And we introduced the CPW transmission lines, and I decided for you to put in there, you remember I did it by hand, but I wanted to show you how we measure them. This is here a probe station. This is a probe station. That's where we put the device under test in there, and you see how the probes come down, these probes. And in this particular case, which is interesting, I wanted to show you, the incoming line, look at this one, that I will. This line is microstrip, but the probes are coplanar waveguide probes. So what happens if you have a coplanar waveguide probe measuring a microstrip line, you still come down into coplanar waveguide form, which are the three footprints that you have seen, this one, and this one. And the two ends that I put here in solid form, those we bring with via holes to the ground of the chuck. And then, so we connect the ground of the microstrip, which is this one, to the ground, to these holes here, which are, in fact, this is the probe, the way it's coming down. And it's it looks like it's a three-legged probe. In fact, it's nothing else like a simple CPW. They come down, touch the three here footprints. The two external ones are going through vias to the ground, and the internal one goes directly to the signal line, like here. All right, so always on a probe station, same thing here. On a probe station, you always come down in a CPW form. So this is how they measure a microstrip. And here it's how they measure a CPW line. You see the grounds of the CPW are this one. And the signal line is here. And the CPW is what at the end? What do you think? The CPW are two slots, all right, where the fields is created. The electric field, just to show you here, if I, for a moment, I'm gonna erase those. The electric field goes like this. Let me be very. The electric field will go like this. here.
Dr. Katehi?
Yes,
CW, is it CW, CVW or
CPW,
CPW?
CPW, coplanar waveguide. And it goes like this here. And what is the interesting thing? Because it goes like that and they are opposite arrows, if each one of them was like a small dipole, and because they are out of phase, all right, they have the opposite direction, they don't radiate. They only keep the field very close to the coplanar waveguide. It's like the microstrip is like this, all right, and the field goes like that. But if there is field like here, and in the microstrip, the field at the edges has this opposite direction. So that's very similar to what you see here. It's like there was a microstrip where we ignore this part, and then we look at this and this. That's what you would see from the top. If there was a microstrip here from the top, and then I could only see the electric field lines from the top. This is my microstrip line, and I use a different color. Then I would see the field lines to go like this in the microstrip. So all of the field is connected underneath it. So coplanar waveguide is kind of similar in some ways. We have, so because they are out of phase, the field concentrates very, very close. It is not radiated, and that is important because if it stays close, it propagates very close to the line. So this is how the field goes, and these are the probes. Oops, the probes are here. This is the ground, the yellow. The dark are the slots, are the openings, all right? So that's a microstrip. So, and that's how they measure it. Another way, another CPW here for your, I mean, another probe station there. Every organization has those probe stations. So wherever you go and work, you're gonna find those probe stations there. Okay, you have those on your computer. And what we did from those, as I said, we put the noise figures on the left, the gain figure circles on the right. And then we looked at an intersection and we decided on the basis of what it was given to us to use this point. Oops, always the same here. All right, and you read your gamma S from there. So then we went down and I said, now that I found the gamma S, which is this one here, what if I try to develop a matching network that is gonna match this gamma S, which in fact, the gamma S is like what I see here, all right? And I wanna go from that to a 50 ohm load, which is this one. That's your 50 ohm load. So practically we did this, I did this problem on the Smith chart. We start from where gamma S is, which is right here. Then you go with the arrows all the way until you see Z in B, B prime, and then you come down to the center of the chart, of the Smith chart, where is your Z naught practically. So how I solve this problem is practically from Z in AA prime, which is up here, to Z in BB prime is a section of line. You see that section here. All right, and then after that to go from Z input BB prime, which is here, to the center of the chart, which is here, you have to add a series load, which is here. All right, and if you do that, then you find, excuse me, let me go back here, you find that your load, which is interesting here, all right, your load is, I have to cancel with this load, Z sub S, all right, look at this one, this equation here, which is important. You always have to place these equations carefully. Your Z in at AA prime, when I read it from the Smith chart, normalized, of course, is 1 plus J 1.35, okay? And what I wanna find out is primarily, I have to, Z input here is 1, all right, Z input at BB prime. What did I say? Z input at BB prime, I should say. Is nothing else but 1 plus Z sub S. And this is exactly what I have on my Smith chart. And the extra for the one, it's 1 plus Z sub S, so Z sub S is 1.35. You see that?
Yes.
So, okay. So now there are two things I need to do. I need to materialize, if I say do this in physically, I will have to materialize this section of line, the Z naught, and then I will have to materialize this Z sub S. Okay, what is Z sub S? Is a reactive load, all right? Is a J something. If it's J positive, as it is here, what kind of an element is there? If it gives me a positive.
Inductive.
Inductive, all right? This Z sub S is nothing else but J omega L, all right? And so, if I go here in these equations, I wrote exactly what I told you, that the Z sub S, without the J here, I just removed the J, all right, for simplicity, is, I removed the J here, is omega L, and that is 1.35 times Z naught because I denormalized, all right? I put the Z naught back into the picture. So practically, your Z sub S is nothing else. The equivalent of omega L is 67.5 ohms. Okay, now from this equation, I can find L at 60 gigahertz. So from this equation, I can find L. And my L from here is 0.179 nanohenries. All right. And now I would have to create this 0.17 nanohenries at 60 gigahertz. I would like now to remind you on something that we found when we were doing the filters. And there is something you need to remember. When you have a high impedance line, so now we are reviewing some of the filters, of how we implement those. When you have a high impedance line, then a small section of a high impedance line is equivalent to a series inductance. All right, so that is the statement that I made here, and I will write it so you remember it. So where am I gonna write it? I'm gonna make some space here.
So, Professor, so
Yes.
are you going with a lumped element approach because at such high frequencies, the like a shunt microstrip
Yes.
with,
Yes.
is like too small?
Yes, yes. So always in high frequencies, like 60 gigahertz, 100 gigahertz above,
Right.
I would
Like,
always go with lumped elements first until I realize that the value of the lumped element is very difficult to create. All right. So if you find, for example, a very large inductance, a very high inductance is it's difficult to do because you need many spirals. So I would not go there if I needed to. But for a small inductance like 0.179 nanohenries, all right, it's just a kind of a small inductance. Yes, I would like to do it in a lumped form first to see. I would like to try to see how it looks.
okay, but say at like a frequency of like 4 gigahertz, it'd be better or more practical with the shunts.
Yes, exactly. Absolutely. Okay. So I would like here to write something so you remember it as a move this up, make it a little smaller, then, and I will do the same thing here, move it, make it a little bit smaller, and then I will write a conclusion in between in red that says that a short section of a high impedance characteristic impedance line is equivalent to what? An inductor. L. Okay, remember that. This is not only true for the low noise amplifier, it's also true for the filters. If you have to do a filter in high frequencies, always try to think of lumped elements first. Okay. Now, how I did this, I wanted to remind you how I did this some time ago. So I will add a section. And what we have is the following. Let me just remind you a few things. We have a transmission line, a section of a transmission line, first of all. Let me start with that. This is just a review. When you have a section of a transmission line, and that's from the equivalent networks that we covered, then, and that's L, Z naught, then this is equivalent to what? To a T or a P configuration. Say, look at the T configuration. They're both in the books, or in the book, in table form, where this one is Z11 minus Z12. This one is Z22 minus Z12, and this is Z12. Well, what is this Z? These are the elements of the Z matrix. What is the Z matrix? Do you remember how we defined the Z matrix?
V1, V2 equals Z times psi1, I2.
Yes. Thank you. So Z, I1, I2. Okay, where this is port 1 and this is port 2. All right. Now I will demonstrate, and then, excuse me, from that also there were relationships for A, B, C, and D. All right, because from Z, you can go to the ABCD matrix. So practically, you have an ABCD matrix here. And from the ABCD matrix that we have for that, we have for some fundamental networks, and one of them is on one of the tables in this chapter. I think, I don't remember what was the number of the chapter, but I think maybe it was 6, something like that. You find from ABCD, then you can find your Z matrix. And from the Z matrix, you can find an equivalent circuit. All right. Now, what I did here, we know for that. We also know exactly the same for a simple series load. If we have something like that, and this is not a transmission line, just a load connected in series. And let's assume that you have here input transmission lines. Input, Z naught here, Z naught there, and that is your, let's call it Z sub S, for example. Then we also have the A, B, C, and D matrix for that. Now, I have that in mind, all right? So I remember that I have the ABCD for that, and my Z sub S, it could be the one that I found here, my J omega L. So since I know this matrix, and since I know this matrix for this transmission line, then if I make those two matrices identical, they're green and they're pink, if I make those identical, so this is for the line, for the inductor, and this is for the transmission line, then practically, by making the two ABCD matrices identical, then practically I equate my transmission line to this inductor. So that's what I did here. I started with the ABCD matrix for the load. And I started with the ABCD matrix for this section of the line. And then, I'm skipping this, I went here, where now I have independently the two ABCD matrices for the series inductor and for the section of line. Now, what I do here, I assume that this is a very high impedance. And I assume also, all right, ZOH means high impedance. H is so ZOH means high characteristic impedance. Okay? So practically, just to change it. So that's that. Then, what else do I assume? I assume that really nothing at this moment. I try to get my ZOH to be as high as possible. So from here, I found that I can find this ZOH, all right, from this relationship. Let me see. Okay, here, look at this one. If I try to make these two the same, then I will assume that 0.9 is very close to 1, which is true, All right. I mean, these are all we're talking when you try to take an ideal transmission line matching network and move it into any form, whether it's microstrip or CPW, you start making assumptions. And after you do the design, you will have to check it out. You will have to simulate it to make sure your assumptions were correct. My assumptions is that 0.9 is approximately equal to 1. That this 0.9 is approximately equal to 1. So in fact, if I make that assumption, I'm good with these two, okay? And then the next assumption, the next two assumptions I will make is that, first of all, I will make the assumption that Z is equal to that, all right? And that gives me L. And then also I will assume that I will select my ZOH to be so high that this ratio that I show you there is very, very small, and I can approximate it with 0. Did you get what I tried to do?
Yes.
Is that clear? Okay. So then, practically, the only thing that I have to do here is to select or to find a ZOH which is high enough. So on one end, I can find my L. And then second, I can find high enough of a ZOH so that becomes very small. And from the values that I had, my ZOH gets a value which is reasonable of 158.8, say 159 ohms, which practically makes this very small because I have to divide 0.4 by 160, say, which makes it a very small number. So practically, yes, under a very high value for ZOH, these two are identical. I can make them identical. And the value for ZOH that satisfies that, and here I put the numbers also for you to see. You see the approximation, all right, that I've made. 0.9 and 0.9, I assumed them 1. 0.003, I assumed 0. And then what remained here is only that, which gave me L, inductance. And therefore, this section of the line that is very small in length, if you can see, has very high impedance at 60 gigahertz, is equivalent to an inductance. So having done that, now I'm going to calculate the physical dimensions. And there are, for this kind of coplanar waveguide, there are these calculators that you can find for free, and that's what I use too. And for the inductance, I found that S here is 20 microns. I found the W is pretty high. All right, is 144 microns because the field concentrates here in the apertures. That's where the field concentrates here. All right, in fact, let me just show you. The field concentrates here. And the field looks like this. So if the the conductors are very close, the capacitance is going to be very high. And that's not going to work because I want this section of line to give me an inductance. So W is going to be large, which means low capacitance is high characteristic impedance. You remember that? That's always true. The fact that Z naught is square root of L over C, where L and C are the per unit inductance and capacitance of line per unit length. Inductance, line inductance, and C is per unit length, line capacitance. All right, so when C becomes small, Z naught increases. Where L becomes high, Z naught increases. When C becomes high, and that implies that the conductors will be close to each other, then your Z naught goes low. Okay, so we found here from this calculator the values. For H, I assume that the thickness is 200 microns. That is on kind of a low epsilon R dielectric around 4. And then I got that S is 20 microns, W is 144 microns. The length is about 3,300 microns, about 3.3 millimeters. Lambda, excuse me, and the length, that's a lambda, the 3,300 microns, and for 60 gigahertz, and the length is 232 microns, okay? And then for the section of the CPW line, I had the distance from, I assume this is my ideal transmission line. I found from here that it's also on the same substrate. That now in this particular case, the W, which is the center conductor, it will have to be only 10 microns. Excuse me, the separation between the conductors has to be 10 microns. The center conductor has to be 50 microns. And the length of the line is 134.4 microns. And the wavelength, you see, changes slightly. Is not identical because the wavelength, of course, depends a lot on how the field develops around the line. So it's not the same, it changes. It changes slowly. It does not change drastically, I mean. And then you find the length here. And how would I make them? Like this. This is my transmission line, where the apertures are very narrow, 10 microns, and the center conductor is 50 microns. And this one is my inductance section, where the center is 20 microns and then the width is about 144. They're approximate. Do you see what I did here with these ones? Here, you cannot go up abruptly from one geometry to another. If, say, I had developed something like this, all right, if I had developed something like this, I would have a high reflection coefficient here from high frequency effects. And this high reflection coefficient here, which is not considered in ideal transmission line on the Smith chart, would change the characteristics of my matching network substantially. So I developed what we call these transition sections. So I try to limit this abrupt transition from one geometry to another by tapering it. This is called a taper. Taper. To reduce the high frequency effects. And that's how my matching network will look in the input port. Now, in the output port, how would we go now? We fix the matching network for the input port. Who can tell me what we are going to do for the output matching network? What are we going to do for that?
We're going to use the source reflection coefficient to calculate the output and the load reflection coefficient, and then kind of go through the same process of using the Smith chart and using a lumped elements approach to matching it.
Exactly. And I will write down for you the expressions. I'm trying to find them from the book. 1 second. Let me see. not here, excuse me, the previous. One second. Okay, probably somewhere here, where it shows how the Z in and Z out are. One moment. Maybe it's better if I find them from my notes somewhere, because in the book it's not very easy. Okay, let me find it in my notes. All right, it should be in week 11. Okay, somewhere before then, 2010. Yes, so let me see. Not there. Ah, there you go. So from gamma in, I guess this is, one second. I apologize for, here we go. These are the equations you have to keep in mind, all right? From gamma, gamma in is a function of gamma L, all right? And gamma out, which is on the, at the output port, at the right-hand side of the amplifier, it's a function of gamma S. Gamma S here has been defined for us. Okay, we found gamma S. It was exactly the point we had on the Smith chart. And from gamma S now you can find gamma out, as your colleague said. We can find gamma out. And now what do you do for gamma L? How do you define gamma L?
Complex conjugate of gamma.
Yes, exactly. Exactly. So now you know gamma L, and then you go and design the matching network in a similar way, like I did for the other one. All right? So you remember these formulas. These are the important ones. And in the book are somewhere, but the book is not, they are not easy to find. They are definitely there, the expressions, but they're not clearly stated. They're always, yeah, in fact, no, they are, you will find exactly those on where it says single stage transistor amplifier design for maximum gain. That's where you find these expressions. All right. Any questions about this? Because with that, we finished our one example. And next time I'm gonna do a different example. Next time I will do the design of an 8 gigahertz low noise amplifier using also a gallium arsenide FET. All right, so we'll do another example, one more. Any questions? What I will do now is I will, it will take me some, I will copy the same question that I had as part, I had three questions as part of the makeup assignment, and I will copy the first one and give it to you. And I will split in this exercise, it's gonna be participation plus accuracy, 3, 30, and 30. I will give you the same number of points. Or in fact, no, as an exercise, I will give you 15 and 15 for this. So I will just, it will take me only a few minutes and I will turn it on right now. So you will have, I would like you to do it until the Wednesday lecture. So you have until the lecture on Wednesday, which is, we start at 1:35, okay?
Do you mean
And
that
for-
there you will assign an exercise now and it's due by the class of Wednesday?
Yes. Yes.
Okay.
Okay. All right. Thank you.
By the way, may I ask a question now?
Yes.
Okay. I am the person who has emailed you for the makeup
Of
assignment.
course.
And,
But I don't. Yes. Yeah. You were one of those who emailed me.
yeah, and
Absolutely.
I mean the problem is, I only need 120 points, but I did.
You asked me,
already-
and I told you I gave you guidance how to do it.
You said I should choose two of the three or do all the three, but I mean the
Yes.
grade is my question to ask. I did all of the three and only got two correct. Then how much do I get? Do I
The
get-
two correct. The two correct.
Oh, so I get full 120. Okay. Thank you.
You're welcome.
Have a good day.
Bye bye.